Good morning. Let's start. Today it's my pleasure to introduce GodofredoIommi from PUC of Santiago de Chile, who will give the talk, Dimension Theory for Continued Fractions. Godofredo, please.
Thank you, Sebastian. Well, let me begin by thanking Lorenzo, not only for the invitation to give a talk here, but also for running this seminar, which I've enjoyed very much over the last few months. So what I would like to discuss here today is it's a couple of examples. I would like to present a couple of examples in which we computed the Hausdorff dimension of certain subsets of the unit interval. And these are sets of points which are defined in terms of certain properties of their continued fraction expansion. So central to all the results that we will present, to these two examples that I want to discuss here today, is the fact that when you decompose a number in continued fraction expansions, you use countably many partial quotients or digits. So in a sense, there is certain non-compactness around the continued fraction expansion, and that's what we would like to exploit in these examples. But well, before going on to the continued fraction setting, I would briefly like to recall some results on decimal expansions, because I would like to compare it with the continued fraction setting later on. So let me briefly recall you. So you pick a positive integer, and every number can be written in base B, the way it's presented there. And the notation we will use is this one here. And in this case, of course, every digit belongs to the set 0, 1, 2, up to B minus 1. You know that there is a map, the multiplication by B mod 1, that acts as the shift there. So that's the way you introduce ergodic theory and dynamical systems to this setting. And this map has the Beck measure as an invariant and ergodic measure. That's all fine. A number is normal in the base B expansion if you pick any string of digits, D1 up to Dm, and you compute the frequency of appearance of that string in the expansion in base B of the number x. And if that frequency it's 1 over b to the power of the length of the string, then you say that the number is normal. So for example, if you're expanding in base 10 and you look at the digit 7, the frequency of appearance of the digit 7 in a normal number is 1/10. So a classical result is that Lebesgue almost every number is normal, in particular in base B. The fact that this result is it's a corollary of Birkhoff's ergodic theorem was pointed out, I don't know, but at least in 1945 by Ries. Maybe it was pointed out earlier, I don't know, but at least since then. So Lebesgue almost every number is normal. However, I mean, showing that a specific number is a normal number is a difficult question. We don't know whether pi is normal in base 10. So that's why finding criteria that allows you to prove that specific numbers are indeed normal it's a matter of interest. And during the 1950s, Piasecki-Shapiro proved several such criteria. I would like to show the simplest and the first of those. So he showed that a number is normal in base B if there is a uniform constant, so that for every closed interval, you look at the orbit of the point x with respect to the map, the multiplication by B, and you count the times that the orbit hits the interval AC, you compute the frequency of that, and the lim sup of that frequency is bounded up above by the constant times the Lebesgue measure of that closed interval. So a Lebesgue number, a normal number satisfies that condition, is an equivalence. So I'm not very interested in the proof at the moment, but I just like to point out how do you proceed. You pick the sequence of empirical measures, pick an accumulation point for it that you know because the space is compact, and essentially the assumption that you have here allows you to show that that measure, that accumulation point, is absolutely continuous with respect to the Lebesgue measure. The Lebesgue measure is ergodic, so you can conclude that actually the measure mu is indeed the Lebesgue measure, and therefore you have that sequence of empirical measures actually converge in the weak star topology to the Lebesgue measure. So the point is normal. Of course, I mean, this assumption here is that what allows you to conclude the result. So I'll come back to this result later on in the talk, but that's basically the idea. It's a criteria to determine whether a specific number is indeed normal or not, and it has been used to prove that certain constants are indeed normal in base 10 or in base 2, or some of the specific cases. So the last result I would like to recall from base B expansions is the following. You pick any number and you expand it in base B. You choose any digit of the possible digits you can obtain, and you define the frequency of appearance of that digit in the expansion of base B of that number x as this number tau j. So you count the number of times that the digit j appears in the expansion, you divide that by n, and if the limit exists, we call that the expansion. Of course, from what I've just told you, the frequency of Lebesgue almost every number should be 1 over b. But it's clear that there are points for which the frequency is different than that. So for example, if you expand in base 10, you can pick the number which is just ones, and for that number, the expansion will, the frequency of 1 will be 1, and the frequency of the rest of the digits will be 0. So Besicovitch and Eggleston consider the following sets. You pick a stochastic vector gamma, gamma 0, gamma 1, gamma b, such that the sum is equal to 1, and you consider a set of points for which the frequency of each digit is determined by this stochastic vector. So the frequency of 0 is gamma 0, the frequency of 1 is gamma 1, and so on. So what they did prove, Besicovitch did for base 2 and Eggleston in general, is that the Hausdorff dimension of that set can be explicitly computed and is that formula that I'm presenting there. There are plenty of ways of proving this result, and I will mention briefly one, which is not the simplest, but it's one that I will be interested on later, which is the following. You can show first that the Hausdorff dimension of that set is actually the supremum of this quotient, which is entropy over log b, where the entropy is computed on the measures, ergodic measures that support that set J gamma. So this quotient here is, of course, the Hausdorff dimension of the measure mu. So what you're looking at is looking at the supremum of the Hausdorff dimension of the measures mu that support the level set J gamma. This is entropy over Lyapunov exponent. Of course, in the case of the multiplication by B, the Lyapunov exponent is constant, so it's just log B. And once you have this formula, you may use thermodynamic formalism to find a measure that actually maximizes this supremum, that attains the supremum. And that measure is the Bernoulli measure given by the stochastic vector gamma. So what you have here in the numerator of the, in the numerator of the dimension is nothing but the entropy of the Bernoulli measure. So the scheme is that you have this set, you prove this variational formula for the dimension of the set, and then you find, by using thermodynamic formalism, a measure that actually maximizes this supremum. So these are the three results that I would like, I wanted to recall from decimal expansions or base B expansions. And I would like now to move on to the continued fraction setting, which is what I am really interested in here today. So, well, as you know, an irrational number can be written in a unique way as a continued fraction. In this fashion, the notation I will be using is this squared brackets. Here, the partial quotients or digits are natural numbers. Again, as in the case of the decimal expansion, there is a dynamical system associated to this, which is the Gauss map, which is defined 1 over x minus the integer part of 1 over x. It also acts as the shift in the continued fraction expansion. It's an interval map with countably many full branches. It has infinite entropy. And it also preserves an absolutely continuous invariant measure, which is the Gauss measure, which is defined that way. So the first example I'd like to discuss is it's an example that is related to the arithmetic averages of the digits that you have in the continued fraction expansion. Kinchin, in his continued fraction book, in the last page, the last result of his continued fraction book, discusses arithmetic averages of the digits. And you can prove that the arithmetic average of Lebesgue almost every point of the continued fraction digits or partial quotients is actually infinity. Of course, again, as was the case in the theorem of Eccleston and Vesicovich, there are plenty of points for which the arithmetic average is not infinity. For example, you can pick the fractional part of the golden mean, which is just ones. And in that case, the arithmetic average, of course, will be 1. So you can consider for any alpha larger than 1, the set of points for which the arithmetic average of the digits in the continued fraction expansion is actually equal to alpha. So that gives you a level set determined by the arithmetic average. So together with Thomas Jordan a few years ago, we proved that the function that the Hausdorff dimension function associated to this set, that is the function that to each alpha gives you the Hausdorff dimension of the set A alpha of points which their arithmetic average is indeed equal to alpha, is a very well-behaved function. It's a real analytic function. It's strictly increasing, and the limit when alpha goes to infinity is equal to 1. So it's a function that increases smoothly towards 1. It can also be proved, and that's essentially a consequence of the proof that we have, is that each set A alpha is a dense set in the unit interval. So basically what you have, it's a very complicated decomposition of the unit interval, and this the Hausdorff dimension function that codes it, it's extremely regular. So it's an interesting It's an interesting fact. You can, however, consider other ways of averaging. You can pick, for example, a number gamma in between 0 and 1, and look at this, the level sets determined by these weighted ergodic averages. So now instead of using the classical arithmetic average, each number I rise it to the power of gamma. And again, you can define the level sets determined by this weighted arithmetic average. And what we prove with Thomas is that the situation in this case is somehow different. If gamma is different from 1, there exists a constant, depending of course on gamma, so that again, the Hausdorff dimension function is real analytic and strictly increasing in the interval from 1 to this constant. And after that, it's all level sets A gamma have full Hausdorff dimension. They all have Hausdorff dimension equal to 1. So it's a curve that increases, and then you have a plateau where everything is constant equal to 1. So in particular, this shows that this exhibits an uncountable family of disjoint sets, each of which has Hausdorff dimension 1. This shows you that, in particular, that having Hausdorff dimension 1 is not something that is too fat. This phenomenon has been observed earlier. This was not by no means the first time that this appears, but this is the fact. So what I would like to stress here is that you have two different types of behavior. In the case of the arithmetic average, you have a very smooth function that increases towards 1. And in this weighted arithmetic average, the situation is different. You somehow hit 1 in finite time, and then you have this plateau where you remain constant equal to 1 from there, for alpha larger than C gamma. So let me make the clear observation that basically what we're looking at here, these level sets, are essentially level sets of Birkhoff averages of the appropriate potential. In this case, you pick the potential phi gamma to which, for the first digits, assigns you the first digit to the power of gamma. So the arithmetic average is just the Birkhoff average of that set, of that potential. Mm-hmm. So what interests me here today is the fact that essentially the shape of the Hausdorff dimension function, alpha going to the Hausdorff dimension of the level sets, depends basically on the behavior of the potential at infinity. So let me, if you want to be more precise, it basically depends on the integrability of the potential with respect to the Gauss measure. If it's infinity, then you have the smooth increasing function. If it's finite, you hit in finite time the Hausdorff dimension 1, and then you have the plateau. But I would like to think of this, I would like to stress this. I think that the right way to think of this is that you're actually measuring the speed at which these things are going to infinity, or you're looking at the behavior of these potentials when you approach 0. That's basically what determines the two possible shapes that we encounter in this example. So in one case, you have the smooth curve. In the second case, you reach a plateau in finite time, and that depends basically on the behavior of the potential at infinity, of how fast do you converge when you go towards 0. Mm-hmm. So that's the remark I'd like to stress. I will briefly indicate, I'm not going to do the proof, but I indicate what would be the ingredients if you want to handle this kind of questions. So let me first define lambda mu, like the Lyapunov exponent of the measure mu. So the first thing we did is to show, again, a formula, a variational formula similar to that what I presented in the case of the Besicovitch example. So the Hausdorff dimension here is again the supremum of the Hausdorff dimension of the measures mu, for which the integral of phi gamma mu, phi gamma d mu, it's equal to alpha. So think of ergodic measures, and this will tell you that the measure supports the level set, and then that quotient that appears there, entropy of the Lyapunov exponent, is the Hausdorff dimension of the measure mu. So again, you're looking at the supremum of the Hausdorff dimension of measures for which support each of the level sets. Once you have this formula, you use thermodynamic formalism to find a measure that actually attains that supremum. So I'll give you a hint of how you would find such measure, but before that I need to recall you what the pressure is. So for the purposes of this talk, the pressure will be defined by this variational formula. It's the entropy, the pressure of a potential is the entropy plus the supremum of the entropy plus the integral of that function, where the measures run over all invariant measures such that you include this non-minus infinity condition so that to avoid problems as having infinity minus infinity in the sum. So that's a pressure function. And how do you find then a measure that maximizes the supremum in the dimension, the Hausdorff dimension part? Well, you study this two-parameter pressure function, a function that takes Q and delta and assigns the pressure of Q times phi gamma minus alpha minus delta log of the derivative. Why would you look at a function of this type? Well, the first remark is that if you compute the derivative of the pressure with respect to the parameter Q, what you obtain is this integral here, the integral of the function phi gamma with respect to a specific measure, a so-called equilibrium measure, minus alpha. So if you want to find measures that are supported on the level sets, what you have to do is to find parameters for which the derivative at Q is equal to 0. Because in that case, the integral of phi gamma will be equal to alpha. So you want to find then points Q for which the derivative is 0, because in that way you will be finding measures mu Q for which support the level set. And the second ingredient, once you have those measures, is to try to find that not only the derivative at that point is 0, but also the pressure is actually 0. If the pressure is indeed 0, then since the derivative is 0, this part will not show up in the variational principle, and the only thing that will show up is the entropy plus delta times the Lyapunov exponent. So this delta will be again the Hausdorff dimension of the measure mu Q. So I'm not going to do the details, but what I'm telling you basically is that if you look at the pressure, that pressure function there, and you find points where the derivative is 0 and the pressure is 0 simultaneously, then what you're actually finding are measures that are supported on that set, and on top of that, you have a formula for their Hausdorff dimension. You can compute the Hausdorff dimension. So mixing these ingredients, you basically are able to find find a measure that attains that supremum. Okay, so that's the aim. We have the variational formula, then we want to find measures that attain the supremum, and in order to do that, we study this type of functions. This type of functions were studied, I don't know, by Urbanski and Stratman, by Barreira and Sosol. I mean, people have studied this before, and basically the idea is to combine these two features. The fact that the derivative zero provides you a measure that supports the set, and the fact that the pressure zero allows you to compute the Hausdorff dimension of that set. But, I mean, it doesn't really matter. I mean, so in this example that I'm showing here, we have two behaviors. And the behavior essentially depends on the way the potential that determines the level set behaves at infinity. I would like to recall basically examples where this phenomenon has been obtained and discussed in a different setting. Several people have studied related questions with different level sets for non-uniformly hyperbolic maps, say Manville-Pomot map. In the Manville-Pomot map, you have a two-branch system where the derivative is strictly larger than 1, everywhere except at a fixed point where the derivative is equal to 1. So there's this bad set, which is the fixed point at 1, where things do not behave well. So for this class of systems, several people have studied this Hausdorff dimension function for different potentials. For example, Nakaishi, Polycott and Weiss, Gelfert and Rams, Johansson, Jordan, Oberg and Polycott, among many other people. And what happened in their case is that when you again find in certain cases these two different shapes. Sometimes you get a real analytic curve, and sometimes you have a plateau. The situation is not exactly the same because in those cases, the domain of the Hausdorff dimension is bounded. For example, if you're looking at level sets determined by Lyapunov exponents. But again, you observe this phenomenon, strictly increasing real analytic maps or plateaus. And what determine in their cases whether you have a strictly increasing real analytic curve or a plateau is the behavior of the potential at the parabolic fixed point, at the bad set. That's essentially what rules the shape in those examples. So there is obviously an analogy here, and the analogy here is that the infinity, in the case of the Gauss map, plays the role of the parabolic fixed point in the Manville-Pomot case. Or in other cases, if you want to find more complicated bad sets that rather are just a fixed point. But that's the point I want to make. So here, the Gauss map or some other countable Markov shifts or whatever, which are systems that are well behaved, but defined in a non-compact space, what plays the role of the bad set, what plays the role of the parabolic fixed point, for example, is somehow infinity. It's the behavior at infinity what determines, at least in these cases, the shape of the Hausdorff dimension function. That's what rules basically the shape of the map. Okay, so that's one example that I wanted to consider. So we had this arithmetic averages and weighted arithmetic averages, and we looked at the Hausdorff dimension function, and we found two possible shapes, and a strictly increasing one, and one with a plateau. And that shape was determined, was ruled by the behavior of the potential function at infinity, in a similar way as what happens when you study level sets determined by Lyapunov exponents in the case of Manville-Pomot. in that case, in Manville-Pomo case, what rules the behavior what rules the shapes is the behavior of the potential at the parabolic fixed point. In this case, is what happens at infinity. Okay, so the second example I would like to discuss here today has to do with continued fraction normal numbers. So let me just give you the definition. We say that a number is continued fraction normal if the frequency of appearance of every string of digits, d1 to dm, in the continued fraction expansion of a number is equal to the Gauss measure of the cylinder d1 dm. The cylinder d1 dm is the subinterval of the unit interval for which contains all points for which the first digits are indeed this d1 dm. This is essentially the same thing you do when you consider normal numbers in the decimal expansion. It's the same definition. In this case, it's less neat because you're using the Gauss measure instead of the Lebesgue measure, but well, that's a classical definition of continued fraction normal. And again, by Birkhoff, we have that almost every number is Lebesgue, almost every number is continued fraction normal. Again, determining whether a specific number is normal or not in this continued fraction setting is not a simple question. Again, we don't know whether pi is normal or not. And people have constructed continued fraction normals for have constructed points that are continued fraction normals. For example, using the same method as Champernowne. Champernowne showed that the number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 is normal in base 10. And that, so you concatenate all the natural numbers. That construction was also performed in this setting by Adler, Keenan, and Smordinsky. So they adapted that construction to build continued fraction normal numbers. But still, I mean, you might construct one, but if I give you one, it's not easy to determine if the number is indeed continued fraction normal or not. So having a criteria like the Piasecki-Shapiro criteria that was established for decimal expansions is also something that can be interesting. And that was done. These authors, I don't know how to pronounce, but these first authors, Mochevitin and Shredov, I don't know how to pronounce that, they adapted the arguments developed by Piasecki-Shapiro to this continued fraction setting, and they tried to translate somehow the same proof. They said that a number was continued fraction normal if, again, for every closed interval, if you compute the limb sup of the frequency of visits of the orbit of the point X by the Gauss map to that closed interval, that was bounded above by the Gauss map, the Gauss measure of the interval A, the closed interval AC. So they reproduce basically the same condition that was stated before, and they claim that the number was normal in case that condition was satisfied. There was a small gap, there was a gap in that proof, and that was fixed by Aidy and Mans last year. And the gap has to do with the following example. If you pick a number 1, 2, 3, whose continuous fraction is just 1, 2, 3, 4, 5, and things that grow, then the sequence, this sequence of empirical measures has no convergent subsequence in the open interval 0, 1. It actually goes to 0. And the frequency of appearance of every string is equal to 0. Nothing, this grows and grows and grows. So in order to fix the argument, you just needed to ask that this sequence, every convergent subsequence of this empirical sequence, actually converges in the open, half-open interval 0, 1. Once you have that, the same argument that I mentioned at the very beginning of the talk actually holds. You pick an accumulation point for that measure, and then you can show using the assumption there that it is absolutely continuous with respect to the Gauss measure. The Gauss measure is ergodic, so the limit point of the empirical measures is indeed the Gauss measure, and therefore, I mean, everything works, the number is known. But you require to add this condition because it may happen that the mass of this sequence of measures actually escapes out of the system. Might go to 0, basically. So, but if you add that condition, the tightness assumption, tight means that you have all converted subsequence converge in that set that I've specified here, the half-open interval 0, 1. I think that assumption, basically a similar proof goes through. So during this lockdown, together with Aníbal Veloso, we thought of these following sets, basically inspired by the results that I've just mentioned. So we said that pick a number in between 0 and 1, say 1/3 or whatever you like. We say that a number is alpha continued fraction normal if the frequency of appearance of every string in that number is alpha times what is predicted by the Gauss measure. So if alpha is 1/3, the frequency of appearance of every string will be 1/3 of what you have in a normal number, okay? And we denote that set by G times alpha mu G. So again, as is in the case of continued fraction, of normal continued fraction numbers, you might want to construct specific numbers in this case that belong to this set. And you can do this using combinatorial arguments. But there is another way of constructing which I find more interesting because it holds in a broader class of systems. And it's based on the following remark. There exists sequences of ergodic measures supported on periodic points which converge in the weak star topology to alpha mu G plus y minus alpha mu G plus 1 minus alpha, the atomic measure at 0. The atomic measure at 0, it's out of space for us. 0 is not part of our dynamics. So basically what I'm saying here is that the sequence of periodic orbits somehow loses 1 minus alpha of the total mass. That escapes out of the system, and what remains converges to alpha mu G. This is, of course, very much related to what Mike Todd explained in his talk, where he considered the space of invariant sub-probability measures and defined a topology for the invariant sub-probability measures. So if you want to do that, you would say that the sequence of mu n's converges in a different topology to the sub-probability alpha mu G. And you can forget about the atomic measure at 0. that will be useful in cases in which you don't live in a compact space. But for our purposes, this is fine. And with this sequence of periodic measures, if you glue them together in an appropriate way, you could actually construct a point belonging to this set of alpha continued fraction normal points. So the point I want to make then is that if the ergodic measures supported on periodic orbits are in a sense dense in the space of sub-probability measures, you can actually make these constructions in a fairly straightforward way. But that was not what we were really interested in. At the time, we didn't want to construct just one point. And we actually, this is still work in progress, but this is essentially done together with Aníbal Veloso. We proved that for every alpha in between 0 and 1, the Hausdorff dimension of this alpha continued fraction normal points is actually 1/2. And I'm not going to prove this, but I will show several results that might allow you to believe me that the result might be true. The first of such results, so we're looking then at points for which the frequency of appearance of the digits is a third, a fifth of what it's expected from and predicted from the Gauss measure. So long ago, in 1941, Good proved that if you look at the set of points for which the digits or the partial quotients converge to infinity, the Hausdorff dimension of that set is actually 1/2. Of course, this is related to what I'm talking here because in that case, the frequency of appearance of everything is 0. So it is something that somehow escapes towards, these are points for which the orbit, in a sense, escapes towards infinity. These are points that converge to 0, if you want to think that way. The second result that I think it's relevant in this setting is something that we proved with Thomas Jordan, and it's the following result. If you look at the points for which the Lyapunov exponent of that point is infinity with respect to the Gauss map, of course, then the Hausdorff dimension of that set is again 1/2. So you can think of this as points. Note that the derivative of the Gauss map increases as you approach 0. So basically, what the points that we are considering here are points for which the orbit spends a great deal amount of time near 0, where the derivative is very large because in the end, the average will be infinity. Some people call this collection of points that escape on average. There's a language that is used somehow in homogeneous flows, but it doesn't matter. So these are points for which the orbit spends more and more time closer and closer to 0, so that the derivative in the end is infinity. And there is a third result, which is relevant in this setting, which is now of measure-theoretical nature, which was proved by Fan, Jordan, Liao, and Rams, which is the following. Pick a sequence of invariant probability measures for which the Lyapunov exponent of those measures, the integral of the logarithm of the derivative, converges to infinity. So again, these are measures for which their support is getting closer and closer to 0, because the derivative has to grow, grow, and grow. So in a sense, these are measures that are for which their support is escaping out of the system. The mass is leaking out. So what they proved is that the lim sup of the Hausdorff dimension of those sequences was bounded above by 1/2. And moreover, you could construct a sequence of invariant measures for which the limit of the Lyapunov X point is also infinity, that such that the Hausdorff dimension actually attains 1/2. So basically what you can think of this is, a way of thinking of this is that you're looking at a sequence of invariant measures somehow escaping the system, and what you are bounding here is the amount of Hausdorff dimension that they are taking with them towards infinity. So, I mean, these are the statements, but you might want to interpret them as the Hausdorff dimension at infinity in these cases is actually 1/2, either from the measure theoretical point of view or from the topological point of view in the case of points. So you have these two viewpoints. So the dimension at infinity is essentially 1/2. What you might want to consider, how do you use these results to prove what I've mentioned earlier? Well, basically you have to note that if a point is alpha continued fraction normal with alpha strictly smaller than 1, then what happens is that the orbit of that point spends a huge amount of time near 0 because lots of mass is actually escaping out. And combining these results, you play around and are able to basically show what the result. Of course, I mean, all these three results are, in a sense, captured by the pressure function. Here I'm looking at the function pressure of minus t log time of the derivative. And what happened for the pressure function in this setting is that at 1/2, the pressure exhibits a phase transition. For t smaller than 1/2, the pressure is infinity. And for t larger than 1/2, the pressure is finite, strictly convex, real analytic. And an important feature, though, is that if you approach t with numbers larger than 1/2, so the limit, I don't know, right or left, but the limit that approaches from the finite part towards infinity goes to infinity. So using these properties, you can play around and deduce some of the results that I've mentioned before. Great. So what we have then is that in this example, for these alpha continued fraction normal numbers, what happens is that the dimension of that set, it's essentially, again, determined by the behavior for the Hausdorff dimension at infinity, in a sense, for the Gaussian. So these two examples, the example that I presented at the beginning in the case of the Hausdorff dimension function, we have that two shapes, and the fact that we get one or the other shape was determined by the behavior of the potential at infinity. In the case of this new example, the alpha continued fraction normal numbers, so numbers for which the frequency of appearance of digits is 1/3 of what you expect, or 1/4 of what you expect, or whatever, it's again ruled by the Hausdorff dimension of the system at infinity. How much Hausdorff dimension leaks out of the system. So these are essentially the two examples I wanted to show, but I wanted to make another remark over this seminar we have discussed at least a couple of times the notion of entropy at infinity. That was mentioned in the talk by Mike Todd and also in the talk by Barbara Shapira. And I would like to point out that these results, these remarks, are essentially related to what Mike and Barbara explained us. They can be thought basically as results of entropy at infinity of the appropriate flow. So a simple way to relate this result is to consider, pick a suspension flow, semi-flow, of the Gauss map over, that's the base function will be the Gauss map, and the roof function will be log of the derivative. Do you know that invariant measures for the suspension flow can be constructed as the normalized product of an invariant measure for the Gauss map times Lebesgue, something like this. Mu times Lebesgue. And then you normalize so that it has dimension 1. So Abramov's formula tells you that the entropy of that invariant measure for the flow is equal to the entropy of the original measure, h mu. Mu is the invariant measure for the Gauss map. It's mu over the logarithm, the integral of the roof function. In this case, the integral of the log of the derivative. But that quotient is nothing but the Hausdorff dimension of the original measure. So what I'm saying is that if you're studying Hausdorff dimension questions for the map, it's similar, or at least very much related, to studying entropy questions for an associated suspension flow. So that way, when you talk about entropy at infinity for the flow, you might be talking about Hausdorff dimension at infinity for the map. Okay? That way, this is again something that is known, when you prove results for suspension flows, entropy results or pressure results for suspension flows, you might be able to translate some of those results to results in dimension theory for the base map, due basically to this relation I'm showing you here, which relates the entropy of the measures for the invariant measures for the flow with the Hausdorff dimension of the measures on the base. Okay, I think I'll finish here. Thank you very much.
Thanks, Godofredo. Some questions or comments? A question in the chat, Lorenzo.
Sorry, I have no question.
No? Daniel?
It was me if P depends on X.
Sorry?
Of the definition, the normal numbers. There was a constant P. And this
No, it doesn't depend on X. The
Doesn't
constant doesn't depend on X. It's uniform.
Okay.
You actually show it's 1 in the end.
It's equal to 1. Okay.
No, it doesn't depend on X.
And the second question, why 1/2?
Okay.
How would you need to modify the map to get whatever?
I mean, yeah, that's of course a good question, and it's very specific of the example I'm considering. You might say that 1/2 is the entropy at infinity of the geodesic flow over the modular surface, if you want to make it fancier, but 1/2 is, I mean, it's very specific to the partition of the Gauss map. The length of the intervals are essentially of the order of 1/n squared. So when you compute the pressure function, you're basically summing, making a series that it's 1/n squared to the power of t, and that is convergent or divergent depending whether T is larger or smaller than 1/2. If you pick a different partition and choose a different countable map with countably many branches, you may have a different number. I mean, that's easy to adjust. There is one thing that one has to be cautious of, and is that all these results depend on a property that I didn't emphasize enough of the pressure function of the Gauss map, which is that when you approach the pressure, when you look at the pressure function and you approach 1/2 by numbers larger than 1/2, then the pressure grows up to infinity. The limit of the pressure function when T goes to 1/2 with T larger than 1/2 goes to infinity. You can construct examples of Markov maps with countably many branches in which that is not the case. It might be infinity and then negative. Then the behavior is completely different and the situation is much more complicated. In those cases, somehow the Hausdorff dimension at infinity is equal to the Hausdorff dimension of the total system. In both cases, it could be 1, for example. And then the situation is much harder to handle than.
Yeah, but if you have something topologically similar to the Gauss map and the order of the intervals, the case of the order 1 over n to the power k, then it would be 1/3 or something.
Exactly. You can play around. I mean, that's fine. The only difficulty thing is that, for example, if you have interval of the order 1 over n to the log n squared, then you're in trouble. Because then the pressure is infinity and then negative. And that type of transition is much harder to handle and provokes somehow new phenomena that doesn't occur in these settings. That's a requirement in order to handle this thing. But as you mentioned, those examples in which the decay might be at a different rate, it's perfectly okay as long as the pressure goes up to infinity. That's the technical thing that you need.
So just to repeat the phrase, what you used, that the entropy at infinity characterizes the point of the phase transition? Well,
in that case, yes. Okay. Yes, because basically, if you look at the pressure of minus T times the roof function, the Bowen formula, the formula that Bowen and Ruel obtained, tells you that, at least in subscripts of finite type, a compact setting, then the root at which that point crosses at the point is 0 corresponds to the entropy of the suspension flow. And here what I'm adding is an extra point which comes just before that, which characterizes the entropy at infinity.
Mm-hmm. Okay. Thank you.
Questions or comments? No? We thanks Godofredo again.
Further question?
I'll stop sharing. Okay.
Okay, well, now is the
So I can see you more.
the no coffee time. I don't know if you have some comments or something to. Sorry, let me stop the recording first.